is wrong with my laptop today. Okay. So this is part 2 of our interference curriculum. Part 1 included division of wavefront, production of virtually coherent sources, and then Young's double slit experiment to study the division of wavefront method in detail, and I hope you have gone through the minute details of everything that we discussed regarding Young's double slit experiment, all the calculations, fringe width, etc., uh, condition of brightness, condition of darkness. And then we also discussed two other experiments where the division of wavefront is employed too, that is Lloyd's single mirror and Fresnel biprism. Okay, so that was part 1, and now in part 2 again we will study the same topic, that is interference, but now we'll do interference by division of amplitude. Just keep in mind that the conditions of obtaining interference fringes, if you remember, I had given you 6 conditions that are sort of mandatory to obtain interference fringes, to observe interference fringes on the screen. They are still valid. Whatever be the method of interference, to observe the fringes on the screen, those 6 conditions need to be satisfied. Okay, so let's start interference by division of amplitude. Okay. Now, before we go to the actual topic, the mathematical analysis of how this happens, etc., we have to know certain definitions. The first one of that is optical path. Now, what is optical path? You have shortly encountered this when we did a problem in Young's double slit experiment, where we had kept a transparent sheet, thin sheet of material in front of one of the slits of the Young's double slit setup. Remember, we did that problem and we calculated the shift in the fringes, and we discussed that how that particular experiment, a little twerking of the Young's double slit experiment in the introduction of a thin transparent sheet, how that can help us find out the refractive index of the transparent sheet or fringe width, etc. Now, what we did not explicitly talk about there was this concept of optical path, which we'll do now. Now, suppose we have a source at A and a source at C. Light from the source A travels towards the observer positioned at B, and light from the source C travels towards the observer positioned at the point D. Now, the geometrical distances AB and CD are the same. Okay, both rays AB and CD travel the same geometrical distance, where AB equal to CD equal to L, capital L. Now, a very thin slab of a transparent material of refractive index mu and thickness T is placed in the path of the first ray, that is the ray AB. Okay, so distance is L, AB and CD, and light travels with the speed c, small c, as you all know. So the time taken for light to reach D from C, where there is no other material in between, it just travels in air. If we denote it by tau CD, then tau CD is equal to L by C, distance by speed, okay, time taken. Now, time taken by light to reach B from A, which is tau AB, is L minus T by C plus T by C mu, okay. So, L minus T is the distance traveled in air with the speed c, whereas T, small t, is the distance traveled within the material of refractive index mu, and within it light will travel with a velocity c mu. Okay, just remember that here the Roman alphabet T is used to denote thickness, whereas the Greek alphabet tau is used to denote the time. Please don't get confused. Okay, now this c mu, the velocity of light in the material of refractive index mu, is c by mu, as you all know. Refractive index is the ratio of the velocity of air in velocity of light in air to that in the medium. So c mu is c by mu. So replacing c mu by c by mu, that is replacing c suffix mu by c by mu, we get tau AB equal to L minus T by C plus T by C by mu. So mu goes up, and so the denominator becomes C, and we get L plus T into mu minus 1 whole divided by C, right? Now what I want you to notice is that definitely tau AB is more than tau CD. The time taken by light to reach D from C is definitely lesser than the time taken by light to reach B from A, although in both cases the geometrical distance traveled is the same, that is L, capital L. However, the presence of that thin transparent sheet of a different refractive index in front of the source A in the first case delays the the time of approach of time to the observer at B. It might be very, very small, the delay in reaching B by light from A may be just about a few seconds or microseconds or nanoseconds more than that for light to reach D from C. However, that is a delay. It is a finite delay, as you can clearly see from the expressions here. Okay, you know C is a very high value and C is in the denominator, so the difference might be very less, but nonetheless it is a difference, and tau AB is greater than tau CD. So distance in the first case, in traveling from A to B, the distance traversed in air is L minus T, and the distance traversed in the material, if you look here, L minus T, so tau AB is distance by speed, right? Time is distance by speed. Now L minus T is the distance traveled in air. So the distance traveled in the material is given by mu T. Okay. Now geometrical distance traveled by light in the medium of refractive index mu is T. Thickness of the slab is T. So but the actual distance traversed by light in the medium of refractive index mu is given by mu T. If you look at the expression of distance over here, L minus T is the distance traveled in air, whereas the distance traveled in the medium of refractive index mu is not just T, the value of its thickness, but mu multiplied by T. Okay, so although geometrical thickness is T, but actual distance traveled by light is given by mu T. This mu T is called the optical path. So whenever light travels in a material whose refractive index is not 1, that is, which means not in vacuum or air. So whenever light travels in a medium of a certain refractive index mu, then the actual path covered by light is not just the geometrical thickness of that material, but the geometrical thickness multiplied by the refractive index of the medium. Okay, so when we do the different applications of interference by division of amplitude, we will have to keep this in mind, because we will encounter light traveling in different media. So when the light is traveling in a medium of refractive index mu, we cannot take the path traversed by the ray of light as just the geometrical length, but geometrical length multiplied by refractive index. Okay, so this is the definition of optical path. Optical path equal to geometrical distance multiplied by refractive index, right? Of course, in air mu equal to 1, so optical path and geometrical path becomes identical. Okay, now I want to pause and ask you if you have any doubt over here, because this is a very important concept and I'm not sure whether you have come across it before this class. So I want you to just look at the slide and see whether you have understood it, and if you have any doubt, then I'm giving you a minute. Just see and tell me if you have any question, because this is it's a very important point and we will require to use this very soon. So I hope you have got what I am trying to say. It's nothing to just, you know, learn up. You have to understand that the presence of the material of refractive index mu delays light, and that delay is reflected in the value of the distance traveled by light within that material, and therefore we, to distinguish it from the geometrical distance, we call it optical path. Okay, so is this part clear? Just let me know whether I can move on. Should I move on?
Okay, madam.
Okay. Okay.
Yes, ma'am.
Okay, great. Now the next concept, again, that a sort of a definition that we will learn and which we will again require very soon, is the principle of reversibility of light. Now this is something that you all know, but probably you have not, you know, seen it in print. You've not ever thought that you would actually, you know, sit and have to learn about this. But this is something that we all know by our general intuition. In bookish language, in theoretical language, what is the principle of reversibility of light? A wave motion is a strictly reversible phenomena provided there is no dissipation of energy by absorption. Okay. Now what does that mean? It means that, you know, in very general language, that a ray of light will retrace its original path if its direction is reversed. Okay, this is what I mean by principle of reversibility of light. So if this is the source, please pardon my eye. I mean, I couldn't draw anything better than this. If this is my source S and this is the eye of the observer, if you just interchange the position of the source and the observer, all you need to do is reverse the direction of the arrow, about turn. Okay. Of course, provided that there is no dissipation of light en route, that is while it is traveling from the source to the observer, there is no dissipation. In reality, there is always some dissipation, so exactly the same intensity will not be obtained, but in general this is the rule, and this is the principle of reversibility of light, which we will soon apply. Okay, now comes the third and most important part of this particular exercise, that is what is unique, as well as the most important law when we have to analyze interference by division of amplitude, and that is Stoke's law. Okay, same Stokes who gave us Stokes theorem in vector analysis, but now the law is for optics. Now what is Stokes law? We'll come at Stokes law. First let us, I can't state Stokes law directly because it won't make sense. So I'll just tell you a few more things before we finally arrive at what exactly Stokes law is trying to tell us. Now, when a ray of light is incident at the interface between two medium, remember we were discussing this the other day, that when a ray of light is incident at the interface, what will happen? Part of it will get reflected into the same medium and part of it will get refracted, or now we use the language transmitted into the other medium. Okay. Now, how much of it will be, now for example, if you have a very shiny surface, then most of the light will be reflected and very little will be transmitted. If on the other hand, it is a transparent, it is the interface of air with a transparent medium like say water or glass or glycerine, then part of it will be reflected but most of it will be transmitted. Okay, that is what is known as a transparent medium. Now how is this decided, that how much of light will be reflected back into the same medium and how much of it will be transmitted into the next medium? How is this determined? So there are basically two factors that we can define. The first parameter is designated by small r. This is known as the reflection coefficient. What is reflection coefficient? It is the fraction of the incident intensity that is reflected into the same medium. So when a ray of light is incident on a medium, how much of it will be reflected back is decided by this reflection coefficient R. Okay. And the other parameter is T, small t, the transmission coefficient. As you can understand, this is the fraction of incident intensity that is transmitted into the other medium. So this will decide how much of light will be transmitted into the next medium. So obviously you can understand that the reflection coefficient of a shiny surface is very high, whereas the transmission coefficient of a transparent surface is very high. Whereas if you have an opaque surface, for example, if light is incident on a piece of wood, then you can't really say how much is transmitted. Most of it will be reflected because we can see the piece of wood in the reflected light, but some of it will be transmitted. Okay, so how much? So we are talking in very vague language, some of it, little of it. Okay, so all these are abstract quantifying adjectives. Exactly to know how much is reflected and how much is transmitted, we need to know the reflection coefficient and the transmission coefficient. Suppose reflection coefficient in medium 1 is R1 and transmission coefficient for medium 1 to 2 is T1. So to define transmission coefficient, you need two mediums because light goes from one medium to the second medium. Okay, and suppose reflection coefficient of medium 2 is R2 and transmission coefficient from medium 2 to medium 1 is T2. So remember, reflection coefficient and transmission coefficient are medium dependent, and not only that, for the transmission coefficient, the direction is also important. If you are going from medium 1 to 2, you will have one transmission coefficient, whereas if you are going from medium 2 to 1, the opposite direction, then you will get a different transmission coefficient. Okay, so these few things are new. You have not come across this earlier, but these are things that you need to keep in mind for our next exercise, which will eventually give us Stokes law. Okay, now suppose light of amplitude A is incident at the interface of medium 1 and 2. Okay, and also let us suppose that 1 is the rarer medium and 2 is the denser medium. Okay, so 1 is the rarer medium, 2 is the denser medium. So we will now go through the steps of a certain exercise to arrive at Stoke's law. Okay? And light of amplitude A is incident at the interface. This is the normal, of course. We already said that R1 is the reflection coefficient. So R1 will decide the fraction of the incident wave that is reflected. So amplitude of the reflected ray will be AR1. R1 is a fraction, remember, always less than 1. The maximum value of R1 can be 1. So AR1 is the amplitude of the reflected ray, and T1 is the transmission coefficient when light is traveling from 1 to 2. So the amplitude of the transmitted wave is A into T1. Is the first step clear? So all this while, when we used to draw this ray diagram, incident ray, reflected ray, refracted ray, which we are now calling transmitted ray, we were not bothered about their amplitude. In fact, we never thought about what was happening to the amplitude. But you must now think about it, okay? Single ray is coming, and from that we are getting 2 rays. It is getting divided into 2 rays. So obviously, intensity is decided by the amplitude. Remember, intensity is amplitude squared. So if we are getting 2 rays from a single incident ray, then the intensity of those 2 rays will be lesser than the intensity of the incident ray. Okay? And the intensity, basically the energy, is distributed into the reflected and the transmitted ray. How is it distributed? How much energy does the reflected ray get? How much energy does the transmitted ray get? In other words, what is the amplitude of the reflected ray? What is the amplitude of the transmitted ray? Is decided by the parameters R1 and T. Okay. So this is my first step. Source is here and this is what is happening. Now let us, so this is the incident ray. This is the reflected ray of amplitude AR1 and this is the transmitted ray of amplitude AT1. Now in step 2, what I have done is I have placed my source here, okay, here in this picture my source was here. Now I place my source here, okay. So now, so that AR1 is the incident ray. We have now the incident ray is of amplitude AR1, okay. So reflected into medium 1 again. So what will be the amplitude of the reflected ray? AR1 multiplied by R1. So AR1 squared. And what is the amplitude of the transmitted ray? Still coming from 1 to 2. So transmission coefficient is T1. So incident amplitude multiplied by T1. Okay. So this is the reflected ray of amplitude AR1 square and this is the transmitted ray of amplitude AR1 T1. Is this clear to everybody? Have you understood how we have got these amplitudes AR1 square and AR1 T1? Okay?
Yes, ma'am.
Okay. Now in step 3, I again change the position of my source and now I keep my source here, okay, here, so that my incident ray is of amplitude AT1. So if my incident ray is of amplitude AT1 and part of it is reflected now into medium 2, we saw that we assumed that reflection coefficient of medium 2 is R2. So what is the amplitude of the reflected ray now? Incident amplitude multiplied by reflection coefficient of medium 2. So AT1 multiplied by R2. So now the reflected ray is of amplitude AR2T1. And what is the amplitude of the transmitted ray? Now it is traveling, light is traveling from 2 to 1. So I have to consider the transmission coefficient T2. So incident amplitude multiplied by transmission coefficient of 2 to 1. So AT1 multiplied by T2. So now my transmitted ray is of amplitude A T1 T2. Okay, so I start with one setup and then I change the position of the source so that first in the second step my incident ray is of amplitude AR1, and in the third step my incident ray is of amplitude AT1, and accordingly I get my reflected ray and transmitted ray amplitudes. Now look very carefully at step 4. Now I place one source such that my incident ray has amplitude AR1, so
Ma'am.
that, yes,
Yeah.
so that my reflected ray and transmitted rays have amplitude AR1 square and AR1 T1. I also place another source at this position so that I have another incident ray of amplitude AT1, for which I get a reflected ray of amplitude AR2 T1 and a transmitted ray of amplitude AT1 T2. Okay, so in the fourth step I complicate the situation by keeping two sources at this position and this position. So now I have incident ray of amplitude AR1 and second incident ray of amplitude AT1, so that I get one reflected ray of total intensity AT1 T2 plus AR1 square and one transmitted ray of total intensity AR1 T1 plus AR2 T1. Okay, so what is happening in step 4? In step 4 I have placed two sources simultaneously so that I have two simultaneous incident rays, giving me this reflected ray of total intensity this, and this reflected ray of total intensity this. All right, so this is step 1, this is step 2, this is step 3, and finally in step 4 I have this. Okay, now if the principle of reversibility is to be maintained, then this should be the scenario. What does principle of reversibility say? That if you just reverse the position of the light rays, okay, if you just interchange the position of the observer and the source, then what you have to do is just reverse the position of the rays. So here this was the incident ray, these were the reflected and transmitted rays. If I just change the position such that these are the incident rays, then I should have only one uh, ray coming from both these two rays, if my principle of reversibility of light is to be satisfied. And that has to be satisfied because it basically comes from principle of conservation of energy. Okay, so this must be true. Okay, so this must be true. So in order for this to be true, what do I need to do? Comparing this picture of step 4 and this picture, which should be the actual picture pertaining to principle of reversibility, we must have the total amplitude AT1 T2 plus AR1 square equal to A here, and so that will give us T1 T2 equal to 1 minus R1 square, and the second ray AR1 T1 plus AR2 T1, that should add up to 0. Okay, remember that this absence of the ray here in medium 2 does not mean that the rays do not exist. The rays exist in such a manner that their amplitudes add up to 0 in order that this scenario is maintained, in order that we are not moving away from principle of reversibility of light. And this gives us R1 equal to minus R2. So going through the steps of this exercise, we have got a relation between the reflection coefficients and transmission coefficients of a certain pair of media. Okay. Now we will remember this relation T1 T2 equal to 1 minus R1 square, and we'll discuss this relation R1 equal to minus R2. What does this mean? This means that the reflection coefficient and the in the two media are the same in magnitude but opposite in sign. Okay, which means that the negative sign indicates a phase change of pi. The fact that the reflection coefficient of one medium is having a sign opposite to that of the other medium indicates a phase change of pi, which means there is associated a path difference of lambda by 2. Why? Phase difference is 2 pi by lambda into path difference. So path difference is phase difference is 2 pi by lambda into path difference. So path difference is lambda by 2 pi into phase difference. Here phase difference is pi. So path difference is lambda by 2. Okay. Basically, this is what Stoke's law tells us. So what is the formal statement of Stoke's law? There is a phase change of pi and therefore an additional path difference of lambda by 2 associated whenever there is a reflection backed by a denser medium. Okay. So if you are asked to state Stoke's law, then you don't have to go through this entire exercise that I just presented before you. You have to just say that Stoke's law states there is a phase change of pi and an additional path difference of lambda by 2 associated whenever there is a reflection backed by a denser medium. Okay. The fact that this happens only when there is a reflection backed by a denser medium is experimentally established by Lloyd's single mirror experiment. Okay. Now, there has been no experiment that could prove that a phase change of pi takes place even when reflection is backed by a rarer medium. There is no phase change that happens when reflection is backed by a rarer medium. Only when light is reflected from the surface of a denser medium, then there is an additional phase change of pi associated with it. Okay. So when we calculate the path difference, we have to keep this in mind and incorporate this additional path difference of lambda by 2. So if light is incident, traveling in air and incident on say glycerine or glass and reflected back, then we have to incorporate the additional path difference of lambda by 2. If it is the other way around, it is traveling in glycerine and reflects back from the interface of air and glycerine, then no phase change. Clear? So this is the statement of Stoke's law. Any questions? Okay, then let me carry on. So now we are at a position, we have knowledge enough to discuss interference in thin parallel films, which is actually a phenomena that occurs because of division of amplitude. Okay. Now, you have seen interference in thin parallel films often in your daily lives. Can you guess, or if you know, then can you tell the class where we can see what phenomena can we see because of interference in thin parallel films? Does anybody know in the class? Tell me what this is. What is this picture? What I'm showing a picture here. Can somebody tell me what এটা কিসের picture?
রাস্তাটা যদি জলে ভিজে থাকে তারপর তেল যদি পড়লে তাহলে পেট্রোল পেট্রোল তেল ইত্যাদি পড়লে এইরকম
এইরকম হয়। গুড। এটা
এটা সোপ বাবেলের
soap bubble. And this again is a picture similar to the first one. Now, before going on to the mathematics of thin parallel films, I'll just tell you why this is happening. Okay, where is the thin film? কি বলে রাস্তা জলে ভিজে থাকলে তার উপর তেল পড়লে এরকম হয়। Okay, so basically we are getting colored rings, right? Not very well defined because uh, there is no particular experimental apparatus over here. This is just a natural phenomena. When we do it in a measured and metered way inside the laboratory, we get, you know, symmetric and uh, well defined fringes and all, but this is just a natural phenomena, so nothing is well defined. But what is there? There is air, then there is the oil film, and then there is water. Okay, now this oil film obviously is very very thin, but it is flanked by two media which are rarer than oil, or water is rarer than oil and air is rarer than oil. So when light is getting reflected within this film, then we get to see this phenomenon. Similarly, in a soap bubble, the bubble surface is made up of soap. Inside there is air, outside there is air. Okay, and this soap, the material of the soap definitely is thicker than air, and it is very thin, but it has a finite thickness. The surface of the bubble that is made up of soap is very very thin, but even then it has a finite thickness. So that forms the thin film. Okay. So these are natural phenomena that all of you have seen sometime or the other, and these are results of interference in thin parallel films which happen again as a consequence of division of amplitude. Okay, so let's see what happens in a thin parallel film. So consider we have a film like this of thickness T and refractive index mu, and there is air on either side. Okay, for simplicity now we consider that the film is flanked by air on both sides, and at present we consider a parallel film. Eventually we will study more complicated problems, we'll discuss more complicated problems where the film may not be parallel at all, but even then we'll see what happens. Okay, so light is incident. Let this be the incident ray, which is incident on the interface between air and the film of refractive index mu, and it will be partly decided by the reflection coefficient, partly transmitted within the film of thickness T. Now this transmitted beam therefore is now incident on the other interface between the film and air. So again this will be partly reflected, partly transmitted. Please follow the arrows, okay, the chronology of the arrows as I go on. So we have another reflected ray and another transmitted ray. This reflected ray is within the medium and this transmitted ray is into air. Now if we take this reflected ray, then it is again incident on the interface and therefore part of it will be reflected and part of it will be transmitted into air again. And then again this particular reflected ray again incident at the bottom boundary, bottom surface of the film, and it will again get reflected and transmitted. And so this ray again gets reflected and transmitted. Again this ray gets reflected and transmitted, reflected, and so on. So this will go on. Okay. So what we find over here is that we started with a single incident ray and that is being multiply divided up into reflected beam, transmitted beam, reflected beam, transmitted beam, reflected beam, transmitted beam, reflected beam, transmitted beam, and this goes on because it's a parallel film. Can you tell me until when will this go on? What is happening as this light keeps on getting reflected and transmitted, reflected and transmitted? What do you expect to happen to the the rays that come later on? What do you expect from those rays? Will they be as bright as the incident ray or the initial reflected and transmitted rays? Of course, you don't get to see the rays within the medium. All you get to see are the rays that come out from the medium. Okay. So what do you think about the amplitude of the later rays, of the newer rays? কম না বেশি সেটুকু তো বলতে পারবে। No? You can't say anything about the amplitude? আরে কেউ কিছু তো বলো, ভুল হলে তো আমি ঠিক করে দেব, ভুল হলে তো অসুবিধা নেই।
কম আসবে ম্যাম?
নিশ্চয়ই কম আসবে। তুমি একটা কাগজের টুকরো নিয়েছো, কি ধরো তুমি একটা বড়, তোমাকে আমি অদ্রিজাকে আমি একটা বড় ইয়ে দিলাম, চকলেট, ওই বড় যে চকলেট বারগুলো হয় আমুলের 100 টাকার দিলাম। এবারে অদ্রিজা ওটাকে, আরো সব বন্ধু বান্ধব আছে, ও তো একা খেতে পারবে না, অদ্রিজা ওটাকে দুভাগ করলো, দুভাগ করে দুজনকে দিল, ঠিক আছে, বা দুভাগ করলো না, 3 ভাগ করলো, একটা নিজের কাছে রাখলো, দুটো দুজনকে দিল। এবার বাকি যে দুজন পেলো, ওরাও ওদের কাছে, ওদের পাশেও বন্ধু বসে আছে, ওরাও পুরোটা নিজের কাছে রাখতে পারলো না, ওরাও 3 ভাগ করলো, একটা নিজের কাছে রাখলো, দুটো দুজনকে দিল। তাহলে এইরকম ভাগ করতে করতে যে ধরো লাস্টের দিকে যে বাচ্চারা আছে তারা অবভিয়াসলি অনেক কম পাবে অদ্রিজা যতটা পেয়েছে তার থেকে, তাই না?
ম্যাম
বলো।
হ্যাঁ ম্যাম।
ম্যাম বলছিলাম যে যে নতুন লাইট গুলো ইনসিডেন্ট হবে ডিউ টু কনস্ট্রাকটিভ অর ডিস্ট্রাকটিভ ইন্টারফারেন্স, ওদের ব্যান্ডউইথ গুলো ন্যারো হতে শুরু করবে।
এখন তো আমরা কনস্ট্রাকটিভ ডিস্ট্রাকটিভ ইন্টারফারেন্সের কাছে যাচ্ছি না। we are not thinking about constructive or destructive interference at all now. We are just looking at the amplitudes of the rays. We just want to know what is happening to the amplitudes of the rays. Obviously হ্যাঁ, ব্যান্ডউইথ ন্যারো হতে শুরু করবে, ওদের অ্যামপ্লিটিউড গুলো অনেক কম সেই জন্য। কিন্তু I hope that the chocolate example is fair enough to make you understand.
Yes,
okay.
Yes.
Okay, so now let us look at the amplitudes. Okay, so incident ray has amplitudes A amplitude A, sorry. The first reflected ray has amplitude AR and the transmitted ray has amplitude AT. This again gets reflected. So this reflected ray has amplitude AT multiplied by R, the reflection coefficient. Now since we have air on both sides, and since the reflection coefficient has the same magnitude for a pair of medium, only the difference is in sign, so I do not write R1 and R2. I write just R because the magnitude is the same. Okay. So ATR and transmitted is ATT prime. T prime, I have to differentiate between T and T prime because 1 to 2 and 2 to 1 gives you has different transmission coefficients. Okay. Now this again gets transmitted and reflected ray is ATR square. Now ATR multiplied by R, so ATR square, whereas transmitted ray is ATR T prime again because from mu to air. Again this one is ATR cube, ATR square T prime, ATR cube T prime, and this will be AT R to the power 4 T prime, and so on and so forth. Now remember, T, R and T prime are all fractions. So higher the powers of these parameters in the product, lesser is the value of the product. So mathematically now you can see that the amplitude is continuously decreasing as we go to the newer rays. Okay. Now this portion over here, when we talk about thin parallel films, all the rays that are coming out on the top of the film form the reflected mode. Now why is this called the reflected mode? Because the first ray is a reflected ray. Therefore this entire mode is called the reflected mode. Whereas all the rays that come out from the bottom of the layer form the transmitted mode. Once again, because the first ray in this portion is a transmitted ray. So this entire mode is called the transmitted mode. Okay. Now let's calculate the sum of the amplitudes of all rays in the reflected mode except the first one. And I'll tell you very soon why we are doing this calculation. What do I do? What do I want to do? I want to calculate, I want to add up the amplitudes of all the rays in the reflected mode, barring the first one. I leave out the first one, which has amplitude AR, and take the sum of all the rays, the rest of the rays in the reflected mode. Okay. So that amplitude will be AR, ATR T prime plus ATR cube T prime plus next one will be ATR to the power 5 T prime, etc. So if you take ATR T prime common, then you are left with 1 plus R square plus R to the power 4 plus etc. So this becomes 1 by 1 minus R square. Okay. So we have ARTT prime, and remember when we were approaching Stoke's law, we had found out that TT prime is equal to 1 minus R squared. So 1 minus R squared is replaced by TT prime. So A is equal to AR. So what have we used over here? Here we have used binomial expansion since R is less than 1, R is a fraction. And here we have used the relation TT prime equal to 1 minus R squared. Okay. Why are we doing this? What conclusion do I come to? I see that the sum of all the reflected rays in the reflection mode together is equal to the amplitude of the first reflected ray. Okay? The first reflected ray has an amplitude which is almost equal to the amplitudes of all the rest of the reflected rays taken together. All right. what does this let me do? So amplitude of first reflected ray is equal to sum of amplitudes of all the other rays in this mode, which means, of course, the first one is the brightest. Now I could tell this by intuition too, by that chocolate example, but I have shown mathematically also now that the first one is the brightest. So who does this ray interfere with? If the first ray is a very, very bright ray and all the rest of the rays, now if you look at this picture again, these are rays that are moving in a certain direction. So basically, if you consider wave fronts, then these are wave fronts moving in a certain direction, and then we can expect that interference will happen between these rays. But now we find that the first ray has an amplitude which is much greater than the amplitude of all the rest of the rays. So which ray does this one interfere with? Do we take all the rays? Do we consider something like multiple ray interference? What do we do? So who does this ray interfere with? That is now the question. So again we do some algebraic calculations. Okay, first of all, what is the amplitude of the second ray? ATRT prime. Okay, that is ARTT prime, which, putting t prime equal to 1 minus r square, we get this is equal to AR into 1 minus r square. Since r is much less than a, r is a fraction, so we can neglect r square compared to 1, and so this is approximately equal to AR. Third ray, ATR cube t prime, so AR cube TT prime. So this is approximately equal to AR cube. Fourth ray will be approximately AR to the power 5. Now again, since R is a fraction, so higher the power, lesser is the value of this product over here. Therefore, we can easily see that the rays have increasingly lesser amplitude. Only the second ray, by approximation, can be considered to have an amplitude which is close to that of the first ray. Okay, the second ray has an amplitude which is close to that of the first ray, so they will fulfill the criterion to produce interference fringes of good contrast. Remember, to get interference fringes of good contrast, the rays that interfere must be of almost equal amplitude, and this is the only pair that fulfills that criterion. So we are going to analyze the fringe pattern produced due to the interference of the first two rays in the reflected mode. Okay. So when we do the calculation and the analysis, we will consider only the first two rays. Why did I go through this elaborate exercise? Because I don't want you to have any doubts about the rays that interfere. First of all, you must remember that there are multiple rays on both sides of the film. However, we take the interference of only the first two rays because they are the ones that fulfill the criterion of obtaining contrasting interference fringes. Okay? And you also have to remember Stoke's law, and you also have to remember the concept of optical path when we finally do this calculation in our next class. All right, so I'll end my class today and I'll send you the PowerPoint up to whatever I have done. I repeat myself that these are new concepts, so please go through them carefully to see that you actually understand everything that has been told. Don't keep any doubts in your mind.